This is video 3 of Unit 11. In this video, we'll take a look at what's called the Kinetic Molecular Theory. Now, this is a theory, a bunch of statements that describe the behavior of what we call ideal gases. And you'll see that ideal gases are perfect gases, gases that behave perfectly. And real gases aren't always ideal. So there are 4 points to this theory, kinetic molecular theory, called the 4 assumptions. The first one is that gas particles move in constant, rapid, straight line motion. And this, for the most part, is true. In fact, they move so fast that their average speeds are around 1,000 miles per hour. Now remember, they only move a tiny, tiny fraction of a centimeter before colliding into another atom. And so they're constantly moving, but they're moving at 1,000 miles per hour, roughly, which is pretty fast. Assumption number 2 is that gas particles have no volume, or they take up no space. Another way to say it. Take up, oops. Let's try that again. They take up no space, which means individual gas particles don't take up space. So if you have a box and you have a bunch of gas particles, the volume of that box can be assumed to be empty. In other words, you don't have to count, well, how much does the gas take up. It takes up very, very small amount of space compared to the volume. And this, for the most part, is true. This is why gases can be compressed. You can compress them together and into, eventually, into a much, much smaller space. Assumption number 3 is that gas particles do not attract or repel each other. And this is an important assumption because solids and liquids do have attractive forces. Another way of saying this is that gas particles have no forces of attraction. Particles have no attractive forces. Attractive forces. This is not true of liquids and solids. Liquid particles, we know, have a bond between them, and so do solid particles. That's why they're liquids and solids, but gas particles do not. In fact, you can make a gas into a liquid by pushing the gas particles close enough to where these attractive forces bind them together, is the idea. And finally, number 4, gas particles have elastic collisions. This word elastic means they're perfect transfer of energy. Elastic is a perfect transfer of energy. Elastic. Perfect transfer of energy. And that's why gas particles do not ever slow down. It's kind of strange. In a game of pool, eventually the balls slow down. But with gas particles, they keep flying and flying forever, essentially. Now, what we'll say is that real gases follow these assumptions under ideal conditions, which means under moderate conditions, but not under extreme conditions. So, for example, if you have a very high pressure, the gas particles will not behave as gases. In fact, what they'll do is they'll become probably a liquid. Or if you have a very low temperature, we know that every gas at really low temperatures turns into a liquid. So that's what we mean here. At high pressures or low temperatures, gases don't behave like gases anymore. So we have to be under or within a certain limit. And here's a fun-loving chap decided to go somewhere without a plane ticket. He's probably about to be met by a plane. So this then goes into these 2 definitions. Diffusion. Diffusion is the mixing of 2 gases caused by the random motion. So because gas particles are always moving, they will automatically mix themselves. So here you have 2 types of gas particles, these white spheres and these purple spheres, or red spheres. Eventually, by themselves, the red spheres will diffuse, will spread throughout, and be perfectly mixed with the white spheres. This is called diffusion. Now here it says heavier gases diffuse slower. That's because the heavier the gas, the slower it travels. So if this is a really heavy gas, it would take a while for it to diffuse. Eventually, though, the diffusion will happen. Another concept very similar is called effusion, and effusion is gas particles passing through tiny openings. So a famous example of this is a balloon. A balloon has really tiny openings for gas particles to escape through. This is why, over time, balloons deflate. But if you take a look, here we have an example of nitrogen and helium, and over time, the helium actually becomes smaller faster, and that's because helium particles are not smaller, they're lighter. Recall that helium is lighter, that's why it travels faster, lighter at only 4 grams per mole, so it travels much faster. It's able to find these holes faster. It's not that it's smaller, because we said in our assumptions that gas particles have no volume. So it's not smaller, it's actually lighter. They are lighter. That's why helium escapes faster. There's a law for this, or actually an equation that explains it. We're not going to do much with this equation unless you take upper level chemistry, but it says that the rate of escape of one gas is inversely proportionate to the square root of its molar mass. How about that for a fun equation? So let's go ahead and take a look at the 4 gas laws. Now these are going to relate for us the 4 quantities that we can measure about a gas, which are temperature, pressure, volume, and moles. And each one of them will relate 2 of these, essentially, keeping the others constant. So let's go ahead and begin with the first one. The first one is Avogadro's law. This law relates moles and volume. And what it says is that as moles increase, volume increase. Remember that N stands for moles. And what this essentially means is if you fill a balloon with more gas, more moles of gas, the balloon becomes bigger. And that makes sense. Now this is true if temperature and pressure are held constant. So the other 2 parameters will be held constant. We're not going to allow pressure to increase, or we're not going to heat this up. And the way we represent what we say is if both of these go up, we call this a direct relationship. They're directly related. So if one goes up, the other goes up. If one goes down, the other goes down. They're either direct up or direct down. Now there's an equation for this, and the equation is K equals N over V. And let's show you how this equation shows a direct relationship. If you have some kind of number, say you have 10 over, we'll say 4. 10 over 4 is 2.5. Now if you increase the top number from 10 to 20, then you have to double the bottom number from 20 to 8. And if you do 20 divided by 8, you'll still get 2.5. So in other words, this shows you how a direct relationship is represented mathematically. As M goes up, V also goes up. You'll see the same setup with everything else that's directly related. The second law is Charles' law. Charles' law deals with temperature and volume, and it's also direct. As temperature goes up, so does volume. This makes sense because if you have a balloon and you decide to heat it up carefully, the balloon will expand. The balloon will get bigger because the particles are now moving faster and pushing harder against the side of the balloon. This makes sense. This is also a direct relationship, and the equation for it is V divided by T. You divide numbers anytime you want to show a direct relationship. So if V goes up, T must go up by the same amount to keep this ratio a constant. And we also have to think about pressure and moles being constant in order for this to work. And this, incidentally, is how hot air balloons work. Flight was actually achieved much earlier than airplanes came on the scene, and they did it with hot air balloons. So what happens in a hot air balloon, if you have seen one, is we warm up the air inside with some sort of flame, and that air, because it's warmed up, as the temperature goes up, the volume will go up. So the air expands, increasing its volume. That's why the balloon blows up. But then the density of the air on the inside, because it's hot air and it has much more volume, the density actually is lowered. And so if you have a gas with a smaller density, then it floats. And that's how we create a smaller density gas, by using temperature to decrease the volume. Remember that density is mass over volume, so what you're doing is you're increasing the volume and you're dividing by a bigger number, getting the density to be smaller. So that's an application of Charles' law. The next law is something called Gay-Lussac's law, and this was actually determined or formulated by two scientists, Mr. Gay and Mr. Lussac. That's why it's the Gay-Lussac's law. And it deals with pressure and temperature. It's also a direct relationship. As pressure goes up, temperature goes up. Now this may sound strange to envision, but if you were to suddenly increase the pressure of a gas, the gas gets hotter. You can think of it in reverse. As the temperature goes up, the pressure goes up. That makes sense. If you have, say, a closed container with a bunch of gas, and if you heat it up, what will happen to the pressure inside that? Like a canister, the pressure will go up. The danger is that the canister will explode. So as temperature goes up, pressure goes up, but then you can easily reverse it and say that means as pressure goes up, temperature goes up. So if you can suddenly increase the pressure, and we'll show you this, an example of this in class. If you get a gas and suddenly increase its pressure by maybe compressing it, you'll get the gas to be hot. And it's a direct relationship, so same formulation. K is P over T. You could have also reversed this and said T over P. You can easily reverse these, and it'll still give you a constant. That's how we represent a direct relationship. And then V and N are held constant. This, by the way, is what our air conditioning systems are based on. So in an AC system, what happens is gas gets compressed, so the pressure of the gas goes up. There's a special motor inside of here that compresses the gas, and then the gas is funneled outside, to the outside, and the pressure suddenly decreases. Gas is allowed to decrease in pressure, and as that happens, because it's the direct relationship, the temperature decreases. Now, as the temperature decreases, the gas gets colder, and then the gas is routed back into the house and cools the house. So this Gay-Lussac's law is actually used to make a very comfortable living space inside, especially in the summertime. So very important concept here. And finally, we have Boyles Law. Now this is the only law that's inverse. So as this deals with pressure and volume, and as pressure goes up, volume comes down. This is an inverse relationship. So the two are inversely related. And the way to think about this is if you take a balloon, here's a balloon, and if you were to suddenly squeeze the balloon really, really tight to make it into a smaller balloon, maybe you had very strong hands or you had a machine that did this, the volume would go down. So here the volume, we'll say, is 5. Here the volume is 1. Here the pressure could be 2, but here the pressure is 10. Pressure goes up because you're squeezing all the particles now into a smaller space. They're bouncing around much more strongly, you could say. We're hitting the sides of the container more and increasing in pressure. And this is an inverse relationship. So if you cut the volume by 5, you increase the pressure by 10, is the idea. And that's what this equation actually means. If you take a look, this equation shows you an inverse relationship. You multiply your two variables to get a constant. So if this is a 10 and this is a 2, for example, you get yourself 20. Now what if you decrease 10 to a 5? Now you get 5. You have to increase 2 up to a 4. If you reduced 1 by 2, so if you divided this one by 2, in other words, you have to multiply this by 2. And that's how you get your 20 still, as long as temperature and volume stays constant. So these are the 4 laws. The last thing to say on this video is that we can graph the laws, and we'll do an assignment in this. A direct relationship shows a graph that looks like this. So the temperature, as the temperature goes up, the volume goes up. So if you're at this point, say at a certain temperature, 10, and a certain volume, 10, as you increase the temperature to 20, the volume increases to 20. That's kind of the idea. Now, an inverse relationship doesn't look like a straight line. That's not how an inverse relationship looks. It is actually a curve. And this is due to the fact that PV equals K. So if you were to solve for V, V will equal K over P. And this is a Y equals 1 over X graph, if you've taken this in math class. And you can see the same thing here. Say our pressure is 1. And our volume is 5. So if you increase the pressure, you increase the pressure to 2, your volume goes down to 2.5. That's the idea. So I know this is a long lesson, kind of in-depth. So think about the concepts presented here, and we'll practice a lot of this in class. This completes for us lesson 3 of Unit 11.